absolute value, or at most as big absolute value as z. That sort of also makes sense, right? Because the absolute value of this is just like a squared, and the absolute value of this is like a squared plus b squared. It can only be bigger. It can be equal. And then the absolute, and this is the interesting one, is this is less than or equal to z plus w. Right? And this is called the triangle inequality. And if you ever wondered, well, I mean, you guys know why it's a triangle inequality, right? Because you think of this as the side of a triangle, and this is the side of a triangle. This is like vector addition. I hate. I mean, my advisor said something really mean about it once. That's why. He said it like. He always makes fun. I mean, this is mean. So maybe I should say. It's just pretty mean. But the point is, it's triangle inequality. Because if this is z and this is w, well, z plus w is. So z plus w is the sum of the two is over here. But z and w form the sides of, this is z plus w. They form the sides of the triangle. So all this is saying is that the length of the sum is less than or equal to the sum of the individual lengths. As in, the sum of two sides of the triangle is always bigger than the third. That's all it's saying. That's why it's a triangle inequality. Okay? Cool. I'm assuming you knew stuff about this, but I mean, if you want me to prove any of these are all just computation. I can just leave these to you guys. I think you guys can do those. The only one that's sort of interesting, I guess, is C. But anyways, I just wanted to get to the big theorem, just the Cauchy-Schwarz version for complex numbers. I'll prove that and we'll call it a day. So theorem. So this is Cauchy-Schwarz inequality. So take this list of numbers, so take these AI and BIs, the B and C. I'll tell you what I mean. So I have this list of numbers, A1, A2, all the way to AN. I have this other list of numbers, B1, B2, all the way to BN. All right, so this is what I hate about this statement. If you guys have taken linear algebra, you've seen this proof, but like from the sense, think of this as a vector in Cn. That's really what they're trying to make you do. Fine. But it turns out that the sum from I equals 1 to n, so I'll get the absolute value in there, of AI, I shouldn't put I, I should put j, now we have complex numbers. J equals 1 to n of AJ, BJ conjugate, the sum of all these guys, an absolute value squared, is less than or equal to, or yeah, I'll put it this way. The sum of the AI's, absolute value squared, times the sum of the BI's, I'll put in the J's. BJ's absolute value squared, and this is from J equals 1 to n. That's all it says. Okay? And it doesn't, I mean, it's not an obvious thing, but like you don't understand. So this is probably the most important inequality in all of analysis, in the sense of the following. Anytime I read an analysis paper, like a result by somebody in, I don't know, Italy or someone from New York, it doesn't matter. Every single one of them uses the Cauchy-Schwarz inequality, and that's the only inequality everyone always cites. You can go through almost any paper, open it up, and you'll find the Cauchy-Schwarz inequality, because they know everybody knows it, and it's just almost such a joy to get to use this inequality because it's so straightforward. So, are you guys comfortable with inner product spaces from linear algebra? One way of saying this, so this you can't tell, but this looks like the inner product between some vector A, whose entries are this, and some vector B. All this is saying is the absolute value of the inner product is less than or equal to the norm of A, oh sorry, this squared, is less than or equal to the norm of A times the norm of B. This is, and this translates into, so the proof for this will carry over and prove the one I skipped before. Because this is going to prove it for any complex numbers, and the previous one was for real numbers. So it's covered. Does that make sense? So I'm going to give you guys an option, because again, I like you guys. Do you guys want to see like a linear algebraic proof, or do you want to just see like blast it out with analysis, just like put symbols everywhere and it works? Analysis? All right, we'll do Rudin's proof then. I also have a version that's from like linear algebra, which is like uses a little bit of the algebraic structure, but it's not too bad. They're just both kind of like the same. It's a completely opaque proof. So I'm just going to basically copy it out of my notes, but you just put a bunch of symbols in and you manipulate them and then they work. You're like, oh look, it worked. Life is good. But okay. So let's prove this. So this is Verdon's proof. I'm just going to follow his proof then. So would you guys kill me if I don't put the index on all the sums? Can we just assume j goes from 1 to n for all my sums? Cool. aj squared. So I'm going to use his notation even. It's actually pretty straightforward. It's just kind of a mess. Okay. So we're going to let a, b, and c be the sums of everything. Now, I don't even exactly understand why this is where you go first, or why you would go here at all. But he says consider the sum of this. So again, consider the sum of this combination. This is literally the sum of all the b's. This is the sum of, this is the pairwise thing paired with this. And we're going to make sense of it in a second. Okay? So the first thing you have to realize is this is the sum of a bunch of absolute values. So what? If I add up the absolute values of a bunch of numbers, what can you tell me about it? It's non-negative. To be frank, because everything could be 0. But yeah, this can't be any less than 0. Right? So, okay, let's go through horrible computations then. Right, so now we're going to use definitions. I probably could do this off the top of my head. But yeah, let's just do it off the top of my head. So we already have a nice little definition over here for what this means. So we're going to write this as the sum of Baj minus Cbj times Baj minus Cbj bar. Right? That's the definition of the absolute value squared. I wrote it over there. Cool, let's keep going. And this is just going to be the sum of, so, okay, I'm just going to copy everything. I'm going to make you guys do a little work. How can I simplify this bar? Well, first of all, we know we can split it up between the two of them, right? But what else can I do? So what's the conjugate of Baj? So technically, I could always just write this, right? Well, let's just do the naive one. Let's just put a bar on everybody. Okay? This is correct. But I claim one of these bars is unnecessary. Which one? Why is the B unnecessary? Yeah, B is a real function, right? We're taking the sum of a bunch of non-negative real numbers. So this is a real number, so in fact this is just equal to B. Cool. Nice and easy, let's keep going. So now we just do a bunch of, we FOIL out everything and we get mad at each other. But anyways, we get here B squared times AJ times AJ bar minus, oh gosh, I have to contract BC AJ bar BJ minus BC bar AJ B bar plus CC bar B BJ AJ this is bar. And then I'll put parentheses here. I didn't make a mistake, did I? This is a completely opaque proof. I love it. This is how it goes. Let me keep that guy up because I'm going to use him at least close far. Okay, cool. So how can I simplify what I've written over there? Well, so let's just break it up. So the first guy I can write it as B squared times the sum. Now the sum of AJ bar. What's that? It's the sum of the AJ squared. Yep. The second guy, I can break it up as BC times the sum of AJ bar BJ. We'll deal with that in a second. Then we have another term that looks like BC bar sum of AJ BJ bar. And then let's deal with the last term as well. The last term is going to be, so it's CC bar. That's the